So, we continue to solve this problem, right. So, first we find out f. So, what was f? Omega by 2 alpha, and this is for first harmonic. So, what is the value of omega? Omega is twice pi by p. Now, your everything is in watt, which is joules per second. So, period must be expressed in second, and our periodicity is 24 hours. So, 3600, and 2, if you are using radians, calculating the angles, you must be using radians. If you use 2 into 3.14 etc., then you must use a radians. In a calculator, change it to radians, right. If it is in degree, then you will have all kind of erratic results coming in. 180 it would be instead. So, 2 pi by 3600, that is your omega, and alpha would be how much here? Alpha is k over rho c. So, k is 1, rho is 2000, and c is 1000. So, this is simply 5 into 10 to the power minus 7, 5 into 10 to the power minus 7, right. 1 by 2 into 10 to the power minus 6. So, 5 into 10 to the power minus 7, right, and find out f. So, alpha is 5 into 10 to the power minus 7, omega comes out to be 7.27 into 10 to the power minus 5, because that was coming to be 2 pi divided by 3600 into 24, sorry, 1 hour 24 hours. So, into this is what it is. So, this will come out to be this, and f is omega by 2 alpha, and omega is if you calculate this out, divided by 2 alpha minus 7 minus 5, it comes out with 1. How much is L? 100 mm, in meter it will be 0.1. So, comes out to be 8.8528, 8.5. So, now the question of finding out, Z1, which is FL plus IFL, can be written as 0.8528 plus I 0.8528. And now you want to find out cos hyperbolic this complex of this complex number 8528 plus I 0.8528, right. Now, cos of x plus IY, I do not know whether I have it here. Okay, so let's do it. So, cos hyperbolic x plus IY, because it's of the same kind, although x and y are same. Now, this will be what? This you can write like this: e to the power x plus IY minus e to the power minus x plus IY, and whole thing is divided by 2. So, this will be written as e to the power x into e to the power IY minus e to the power minus x into e to the power minus IY, something like this. Oh, it's plus, here is plus, yeah. So, I can take actually what I can take common, I won't take common so far. I will write it as e to the power x. What is e to the power IY? Cos y plus I sin y. And what about this e to the power minus x? Cos y, and this was this fine or this wrong?
Sir, in the third line.
This is plus minus I sin y, right? This is fine, minus I sin y. So, you see cos y can be taken out. So, if I take cos y common, I get e to the power x plus e to the power minus x, and obviously there is a 2 half appearing everywhere. So, there is 1 by 2 everywhere. So, 1 by 2 is here also, right. Everything has to be divided by. Similarly, sin y I can take common. So, it will be minus or plus if I write it I, right, and sin y I take it out, then I will get e to the power x minus e to the power minus x divided by 2. So, this becomes cos y, and what is this? Cos hyperbolic x, and this becomes sin y, sin hyperbolic x. So, this will be written as cos y cos hyperbolic x plus I sin y sin hyperbolic x, right, and then I can erase out most of it. This derivation is simple, not very far, So, oh sorry, this is wrong. This is cos y, right. So, that is what it is. This is the final result. So, you see cos FL plus IFL you can now calculate out. So, that is what I am saying, it is amenable to hand calculation. So, you can do hand, you can write a program for this also, that is not a problem. Just writing simple MATLAB program is very easy. We were doing it in our good old days, Fortran 4 or Fortran 77 C or whatever it is. So, this is how it is. So, this will be cos hyperbolic FL plus IFL will be simply cos FL all in radians plus and then cos hyperbolic FL in this case, because x and y are same, plus I sin FL sin hyperbolic FL. Right. So, this will be your A. A can be easily found out in this manner, right. Let us just do the sin hyperbolic x plus IY, and after that I suppose you should be able to solve them easily, all right. So, this is again available in any basic maths, Krasik, Arvind Krasik engineering maths. That is a good book, you can look into it, pretty old book, but good one, you can look into it. So, I will come to now sin hyperbolic x plus IY. Do the same thing, it will be e to the power x plus IY minus e to the power half would be there x minus IY, and again I write like this, half e to the power x into e to the power IY minus e to the power minus x e to the power into e to the power minus IY, and e to the power IY, this is all there, half e to the power x, this is cos y plus I sin y, de Moivre's theorem, minus e to the power minus x, and this is cos y minus I sin y, and take coefficient of cos y again, you will get half. So, if I take coefficient of just erase some of them out, just erase this out, all right, and rewrite something, write this again. So, I will have half still remaining there, and cos y into e to the power x minus e to the power x minus x, this is minus x minus x, this is one term, and then there is a sine term will be I sin y plus I sin y, and inside would be e to the power x plus e to the power minus x divided by 2. So, you find that this becomes, what is this? If I just rewrite it like I did earlier, it will be cos y sine hyperbolic, yes, sine hyperbolic x plus I sine y cos hyperbolic x. So, that is it. Use this formulae to find out. Instead here I will have FL. So, in my case for M12 and M21 I will have to do that, and this will be FL, this will be also FL, this is FL and this is FL. So, you can calculate this out. If you do this exercise, then I get values of, if I do this exercise, I get values of M0, M1 first for the layer, solid layer, this values comes out. One can try this out, there may be mistake in this, one has to check this, do this calculation oneself, and then you get cleared, right. This is the arithmetic I am not doing, calculators everybody can do it. M0, what will be M0? 1 minus 1 by H naught. Now, H naught was 15. So, this is 1 by 15, 0, 1, and Mi, because it boundary layer, remember it was 1 minus 1 by H, no, H 0, 1. So, I am just doing this. So, that is what it is. And my solid portion matrix is here, 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 and from this, you have to do this exercise. I think I have explained you, unless you do it you won't get it, please do it yourself and you will get it. So, overall transmission matrix will be multiplication of these matrices, and that would give you something like this. One can multiply the matrix easily and you can find this out, right. So, that is one of the example calculation, you do it, so you get it, and finally after multiplication you get something like this. Okay. So, that is the overall transmission matrix. Overall transmission matrix, one has to do this calculation and verify, that is important, otherwise you do not understand how it is being done. Now, we still do simplification. Matrix calculation we have to do, we have to find out ABCD. But if I am interested in finally finding out, let us say, internal temperature of the room, right. In that case, I do not have to solve this matrix even. I can define certain response factors and make use of them. Okay, let us see how we do it. Oh, let us see how we do it. Let us see how we do it. Frequency domain response factors. We define a response factor called decrement response factor, right. We define a decrement response factor. Now, actually what we are doing is, okay, before I tell you about these factors, let me explain the philosophy. Supposing I give a unit sinusoidal pulse outside, that means its amplitude is unity, period is 24 hours. For our simple calculation, hand amenable calculation, we will neglect the other harmonics, take only the first harmonic. The mean we take and take the first harmonic, and by doing this you are approximating it. But if your objective is to find out what is the best envelope, design the envelope, the fenestration, window areas, glass areas, how much it should be, or similar kind of thing, design the envelope part of it, design the building system, including its orientation, shape, etc., what is the best one. Then what you got to do is, you got to compare between different set of alternatives, right, and find out the best one. So, if you do same approximation to all of them, and if the results are independent of the parameter that you have taken, that is independent of orientation, shape, etc., they do not vary, that means it is a linear system, then error will be similar in all the cases. I have a set of alternatives. For example, long axis parallel to east west, another case long axis parallel to north south. I calculate by a method which is relatively approximate, and it gives me that north south is is better than east to west, long axis parallel to east west. Now, if I do an accurate methodology, use more accurate methodology, and it might still give me it will give the same result, as long as my approximation do not affect my relative outcome. It chooses still the best that would be chosen by the most sophisticated mathematical treatment. Problem remains okay. The other problem is you can mathematically make use of very sophisticated tools, but the pattern of variation of temperature every year is not same. Anyway, you are going to use a design temperature profile, heat flow profile, and so on and so forth. So long as your objective is to design the envelope, even approximation limiting yourself to first harmonic is good enough, because whatever result you get using first harmonic, if you take 6 harmonics, you will still get the same results. Error would be there in the first one itself or by any other more sophisticated mathematical tools. So, approximate treatment is okay as long as you are designing. But supposing you want to calculate out the energy consumption in a given year, you can't do it. Energy consumption in a given year, you must have right kind of a verify. Energy audit you want to do, yearly energy audit. You want to verify actual temperature measurements are available with, and you had the electricity bill or something of that kind. Now, in that case, you need really much more accurate mathematical treatment, because now you are comparing with the real thing. So long as design is the objective, then you have n number of alternatives available. I mean, n can be very large as 10,000 or so, or maybe more, as we shall see later on. But you got to choose the alternative which will show best performance. So there the relative error, as long as they are same, it does not matter. And this is the kind of treatment we do in other civil engineering scenario also. When you do a structural design, you won't find a beam which is simply supported in real life, because if you put it on a pedestal, put a beam, you always assume that it is simply supported, but always there will be some friction. So, fixity or friction, there will be horizontal resistance. So, we actually make system amenable to mathematical treatment for a specific purpose. Here our purpose of this in this course is to look into thermal design of building. I am not interested in calculating the energy consumption per annum. For that, the rover softwares are available, and if you want to relatively compare one solution with the other for yearly annual consumption, the design temperature, again design temperature is taken, which is there in most of the software will have temperatures available for major cities of the world. They have a data bank. You can actually pick them up, or you can give your own input of temperature, yearly temperature profile, and so on and so forth. So that you can do. So here our purpose is design. Therefore, we will only use first harmonic and not beyond, right? We will use only first harmonic and not beyond. And in that case, it becomes relatively simpler, right? So we use certain response factor in that situation. One of them is called decrement response factor. Now, what is the idea? You see, if I have a sinusoidal pulse of temperature outside, it will cause heat flow inside. I have a sinusoidal temperature outside, it will cause some heat flow here. Obviously, the time, if I look at it same time, like this is time is 0, this is t, period p, this is 0, and p will be somewhere there. Actually, it will reach, the heat flow will reach somewhat later. Peak of the heat flow will be later than this time, right? There will be a phase lag, as we call it, or a time lag. There will be lag after which it will reach. And also this peak to peak ratio, this will be less than 1. This is usually less than 1. And this is what we call as decrement response factor. So a decrement response factor as the ratio of cyclic flux transmission. So flux transmission to the steady heat flux transmission. So this, what we do is we divide by steady flux. So cyclic flux is this flux. cyclic flux is applied to fluctuation about mean in external temperature or flux harmonics impinging on exposed opaque surface undergoing transient temperature heat transfer. So, if I have a opaque body like this and is undergoing transient heat transfer, I can talk in terms of decrement response factor either from temperature to heat flux or flux to heat flux, but usually we would be using temperature to heat flux, right. So, I have a unit sinusoidal temperature fluctuation outside. Now, why unit? Because if it is unit, so for that any other one I can find out, and we actually divide this ratio by this. We define, how we define u? U value, if you remember, Q, capital Q was U into A into delta T. So, small q will be U delta T. Small q is a heat flow per unit area, heat flux, and that is the steady heat flow for unit temperature difference, right. So, here we define a fluctuating U. Fluctuating U is nothing but Q peak divided by unit T. Now, supposing this has got some T0 T value and here it is Q, then Q by T, T amplitude, Q is the amplitude, Q by T will give me for unit fluctuation what is the U. So, we define U fluctuating or U swing as T swing versus T swing stands for amplitude divided by or it's other round, Q swing, sorry, Q swing divided by T swing. Supposing I have a T amplitude outside and due to that heat flux inside is Q, peak of the heat flux, then this ratio of Q flux, Q peak, this sign is used for fluctuating because I am using mean and fluctuating. So, this is nothing but U swing, and decrement factor is ratio of U swing divided by steady U. Decrement factor usually denoted by mu, U swing by U, U swing by U. So, this is defined as a ratio of cyclic heat transmission to steady heat flux transmission, and mathematically defined like this, mathematically defined like this, mathematically defined like this, but first let us understand a little bit more. I can have a flux here and due to this flux will change, and this ratio of this by this, if it is flux, or it can be temperature as well, or it can be temperature as well, it can be temperature as well, it could be temperature instead not only the flux but temperature and flux swing here. Corresponding to this, the swing here would be reduced, the peak would shift, so this height is less. So, this height by this height I call as U swing, and that would be same as any point corresponding height, because they are all we are measuring 24 hour period is not changing, that is out as an assumption, period is remaining same 24 hourly and they are also 24 hourly. So, any point if I take this ratios will remain same, ratios at any corresponding point I mean the distance from the peak. So, corresponding point if I take this ratios will remain same, because these periods are I am measuring in 24 hours, here also 24 hours, only amplitude is changing. So, at any point if I take for example this to this ratio or this to this ratio is same. So, that is what we are assuming, and this ratio we defined as U swing, and U swing divided by U steady we call it decrement factor, right. Decrement factor is an important one. So, consequently mathematically defined as Q by U swing is defined as QLT divided by this is how it is. Heat flux per unit swing of outside temperature, for unit swing of temperature outside, for unit swing of temperature outside, right, for unit swing of temperature outside. Okay. So, now I can use the matrix to find out this. Now, these are all complex by the way, because T is complex, periodic, T is complex, Q is complex. I am dealing with the non-steady state situation, I am talking of the amplitude, but ABCDs are all complex. So, they will be ABCDs are complex. So, this ratio will turn out to be complex number actually, because ratios will turn out to be, because this ratio will be complex number. Why? because A, B, C, D, these were all complex number, cos FL plus IFL, etc., etc. And mu is defined as u swing by u. Mu is defined as u swing by u. Consequently, if I know this mu, the absolute value of capital Q swing part of it I can find out. In fact, it will be mu into u, which is u swing into T swing outside, mu u into area into T swing outside. I can find out. The whole idea is to get this mu multiplied by u multiplied by the T swing will give you the inside heat flux, swing in heat flux at a given temperature time. So, this is this ratio. So, that is how it is, and let us see how we find out u swing. Mu can be determined from transmission matrix assuming constant inside temperature. So, T I by Q I, that is what we are trying to find out, Q I by T O, Q I by T O. So, I take inverse of this matrix, then I get T O Q O is equals to A B C D inverse T I Q I, if I take inverse of this matrix, right, inverse of this matrix, right, because I want to find out what do I want to find out? I want to find out Q I by T O for T I being constant, because I am saying it is only the fluctuating part. So, if the inside temperature is constant, how much is the Q I? Q I, that is what by definition this is how I do it. So, T I swing is equals to 0, this is 0. I want to find out the ratio of Q I divided by T O. So, that is why if one way of finding out will be Q I would be C T O Q O, but simpler way would be take inverse of this one, T O Q O is equals to A B C D, right, and this you write maybe some other notation we use D, if what will be inverse of this matrix? A B C D inverse is what? Yeah. So, basically it is leave this out, right, this one you want to find out, and to the power this will be D, simply D, this will be simply D because to the power minus 1 plus 1, right, and when I come to this will be minus C, and this will be A, and this will be minus B, right. So, D B C was written like this correctly, A B minus B, yeah. Why is minus B? Is it correct? Yeah, then transpose, yes, yes. So, D minus B minus C, right, fine, that is okay. So, that is what it is. So, therefore, for T I is equals to 0, this is equals to 0, T 0 is equals to D T I minus B Q I. So, T 0 is equals to B Q I, because I am assuming there is no fluctuation of temperature inside. Outside there is a given simple pulse, and inside the wall it is all steady, there is no change. So, that T I swing part I am assuming it to be 0, and that is how I define as B. So, U swing will be Q I by T O is minus 1 by B, and B is complex. So, it will have an absolute value and it will denote the time lag, because you see it is in complex plane real, imaginary. So, this is your real if T 0 is real, Q I will be somewhere here, Q I will be somewhere here in a complex form, right, because because if this is real, this ratio is complex form. So, somewhere will be there. So, this will have some sort of a phase lag, time difference, right. So, that is it, and mu will be given like this. So, absolute value of mu we can find out and use for our calculation also. So, inverse of m is okay. So, if you see that u is given by this and complex decrement factor will be given by this, mu is absolute of complex decrement factor, phi is angle that you can find out, time lag you can find out, or phase difference you can find out. Now, I think I have the x plus I y, mu is equals to under root x square plus y square, u by minus b is something like this, and tan phi is written in this manner. So that's what it is. So this is how we can find out the decrement factor. Now I think I have got an example, perhaps I have got an example calculation for this. To find out this, what is the actual value of this one? It will depend upon sine of y and x. Whether tan, sine, I mean whether it lies in, if it lies in first quadrant, both are positive, tan phi is positive. If one of them is, because in real and imaginary scenario, everything is positive here, this is positive, this is negative. So real term is, this x is, real term is negative. In this one, both are negative. In this one, y is negative. From that you can find out the angle. So I think again we'll break